Okay, so this is part 2 of the proof, and part 2 of the proof is going from this formula, which tells you how f is evolving, to the solution. And actually, we're not going to just get the final answer here. We're going to get the formula for f of x at any time t. So this is the final answer that we want, but to solve it, we need the intermediate solutions always. So how do you solve this differential equation? That's really what we're doing in this video. Okay, and the first thing to realize is that what we really would like to know is f of script x theta t. So we have a formula for f at any point, any test point x. We can pick our favorite point x, and we know how that's evolving. But the evolution is in terms of f at the training points. So if we're going to solve this equation, we really need to understand what is f at the training points doing. How could we possibly understand what is f at the training points? How could we possibly understand this f of script x theta t? Well, the answer is we're going to plug it in to this equation. So we're going to take the equation we derived in part 1, and the first thing we are going to do is plug in the training points. So, and again, the reason we're doing that is because we know that those are important from the fact that they appear in the evolution. Okay, so here we go. How to solve part 2. Part 2. How to solve it. So, and we're going to do is we're going to plug in x equals x1, x equals x2, all the way up to x equals x and x. These are our training points. And our goal is to understand f of script x theta t, which is this vector of all these points. So f of x1 theta t, all the way up to f of x and x theta t. So if we can understand these, we will be able to understand the evolution. So that's what we're going to do. Plug those in. And if you plug them in, what does the equation say? So let's go back to the equation, scroll up. The derivative is alpha k times the thing. Okay, so what we're going to have, the derivative of f of xi theta t is going to be k of xi alpha k of xx times f of x theta t minus y. Did I get it backwards? Is it y minus f? Let's see. Here it's f minus y with a minus sign, and so the final answer should be y minus f. Okay, so good. I got it backwards. Let's fix it by throwing a minus sign in here. Let's do that. Okay. So that's what it is when you plug in xi. And now if you stack all of these, so let's make this one. So like this is x. If this is x1, and this is x1, and then you do the same thing for x2. So ddt f of x2 theta t. When you stack these, you do this n times, then you have a big vector, which is the vector f of xt. So you can take our scalar equation before and turn it into a vector equation, and what it'll say is you stack these together into a big vector. And what it now says is this, ddt of f of x theta t. So these are all the training points together. So this is an nx by 1 column vector, which is we just stack together all these individual scalar equations. And what you get is exactly this, minus alpha k of xx. This is an nx by nx vector, or a matrix, nx by nx matrix, times f of x theta t minus y. And now we're in business because we have a really nice equation. This is f, this funny vector f of x theta t, and that's the only thing on the other side of the equation that appears that depends on time. So everything else is a constant in time. So k, that's some constant matrix. It only depends on the training examples. Y is a constant. The only thing that's changing in time is f of x theta t and f of x theta t. And it appears once on the left-hand side with its time derivative and once on the right-hand side just by itself. And so you should think of this. This is like the differential equation y prime is equal to c times y minus a, where y is an unknown function we're trying to solve for. So if you took a course on differential equations, what we have here is the matrix vector version of this differential equation, which is just the derivative of y is a constant times y minus a. Okay, this one you can solve. And the first thing you want to do is you want to convert it into an equation like this, where z prime of t is c times z of t. So the minus a is sort of annoying. You just want to shift everything over to get rid of it. And once you have that the derivative of something is a constant times the original thing, the answer is an exponential. Z of t is e to the ct times z of 0. And that's exactly what we're going to do. So we're going to do all these steps that you do in a differential equations 1 class. We're going to do them on this vector matrix differential equation. This is an nx by 1 vector. So step 1, we're going to get rid of this minus y shift just to make things clear things up. And I think in the notes, what letter did I use? I used the letter V. I used the letter V. So we're going to let Vt be this thing, f of x theta t minus y. So it's like the original thing we had, except I've shifted out the y. And the point is that the derivative of v of t is equal to the derivative of f of x theta t. They just differ by a constant. They have the same derivative. So what does this equation become? This equation up here becomes a nice equation for v, which is this, d dt v of t is equal to minus alpha k of x times v of t. At least that's what it should be. Let's double check in the notes and make sure I'm not on the goose chase here. Yeah, okay, that's what it is. So this is a nx by 1 vector and nx by 1 vector. This is an nx by nx matrix. Okay, and the solution to this is just like the world's easiest differential equation. The derivative is a constant times the original function. Here it's a vector matrix version of that, but the answer is still an exponential. So if you've taken a differential equations class with matrices and vectors, you know the solution is, it's just this, e to the minus alpha k x x t times v0. That's the solution. So when you do the derivative of a matrix exponential, the matrix multiplies the thing. That's what you get. So this is just like z prime of t equals c z of t goes to the solution z of t is e to the ct z of t. So that's what it is. This matrix exponential is an nx by nx matrix. This thing is an nx by 1 vector, and this is an nx by 1 vector. Okay, that's the solution for vt. We actually care about f, so we just rearrange this to solve for f now. So v is f minus y, so this says f of script x theta t minus y equals e to the minus alpha k of x x t times f of script x theta t minus y. And that gives us the solution f of x theta t is equal to this stuff plus y. Did I write this in a funny way? Yeah, I should write it like that. Okay, y plus e to the minus alpha k of x x t f of x theta t minus y. So that's the final solution for this nx by 1 vector evolving in time. Okay, so we just finished solving f at the training points, f of x theta t, and we have this nice explicit formula, and we want to convert that into a formula for f of x theta t for any point x. So we've solved it for the training points, and that was possible exactly because the training points appear both in if you do the derivative of the training points, it's written in terms of the training points, you can solve that and get what it is. Now we're going to take that explicit solution and solve for any point. And so the starting point is this equation, which was the punchline of part 1. The derivative of f is equal to alpha k x script x times f of x theta t minus y. So the derivative of any point is given in terms of the training points. We know what the training points are now, so we can plug that in. So you plug in, plug in, plug in, and what do you get? Minus alpha k of x script x times e to the minus alpha k of x x t f of x theta 0 minus y. Okay, so the only time the only place that time appears in this, so we're looking at time dependence, the only place it appears is in this exponential. Everything else, this is at initialization. This is a constant vector. So everything else is a constant. I'll draw the dimensions here. This is an nx by nx matrix. This is an nx by 1 column vector, and this is a 1 by nx row vector. Everything else is constant. And so this equation that we have here is just telling you what the derivative of f of x theta t is explicitly. And this is just like the differential equation y prime of t is equal to c, it's like this equation, e to the ct times y. Okay, it's just like e to the ct. There's no y. So this is the point I want to make, that this differential equation, is the time derivative is just an exponential. And the solution to this equation is this y of t minus y of 0 is the integral from 0 to t of e to the ct dt. And what is that? That's 1 over c times e to the ct minus 1. Okay, so when you integrate starting at 0, you have to subtract 1. That's what it's going to be. And we're going to do exactly the same thing. So our solution is exactly the matrix vector version of this. So we can explicitly get how f is changing by just integrating this guy. So it's a really easy differential equation to solve. Maybe the only tricky part is it's a matrix exponential instead of just a regular exponential. So what is the answer? F of x theta t minus f of x theta 0. It's going to be the integral of all this stuff. Okay, it's an integral. Only the middle bit depends on time. Everything else is constant, so we can pull those out. And minus alpha k of x script x. And we're going to do the integral from 0 to t of e to the minus alpha k of x t dt. Then times this constant thing on the end. So again, the only part that's interesting is this nx by nx matrix integral in the middle. And this integral and matrix exponentials, they obey all the same rules sort of as regular numbers. Instead of having a 1 over c, we're going to have an inverse of the matrix that appears here. So this is just a fact about matrix exponentials. So what's the final answer? Minus alpha k of x script x. Then we have the inverse of that matrix, minus alpha k of x inverse. That's like the 1 over c. That's like the equivalent of what we're doing. Then we have the matrix exponential minus 1. It's going to be minus the identity. So e to the minus alpha k of x t minus the identity times the very last second f of x theta 0 minus y. Okay, and we can clean this up a bit. You have a minus alpha inverse and times an alpha. Those cancel out. But the matrix inverse, k inverse, that has to stay there. And again, this only works if the matrix k is invertible. If not, then it's a slightly more complicated story. So it's some kind of pseudo inverse or something. But we're only going to look at the invertible case here. Okay, so what do you get? K of x k of x inverse. Okay, I guess the minus signs cancel out as well. And then you have e to the minus alpha k of x t minus the identity times f of x theta 0 minus y. And this is the exact formula for f of x theta t for any time t. The result we want is in the limit t goes to infinity. In the limit t goes to infinity, this matrix exponential is going to go to 0. That's as long as this matrix is invertible. That'll definitely go to 0. So in that case, take limit t goes to infinity to get. So in that case, you get f of x theta infinity minus f x theta 0 is equal to, that term just becomes a 0. So you get k of x inverse. Multiplying by the identity doesn't do anything. The minus sign goes there. And you have f of x theta 0 minus y, which is the formula we wanted. So that's where the formula came from. And this formula at an intermediate time theta t also might be useful. The last thing you can do is you can do the exact same thing with the formula for theta t. So you can also solve from dt of theta of t is equal to when we did it. Let's see it. Let's scroll up and find where we did that. Here it is. It was the very first thing we did. So we had the formula for the derivative of theta of t, and it depended only on the vector f of x theta t. So by using the exact formula we had in exactly the same way, exactly the same matrix exponential, you get a very similar formula for theta of t. So I'm going to maybe skip the details of that. You can read it in the notes. Maybe it's worth putting in the video the formula that you get. So d dt of theta of t equals, and it was f of script x theta t minus y times, what did it depend on? I guess phi of x. Does that make sense? 1 over square root of n power. Yeah, I think that makes sense. So let's check if that's right. Yeah, and then if you solve this using the same technique we just did, you get this final answer, which is that theta t minus theta 0 is exactly this, the same k inverse appearing from the same integral of a matrix, e to the minus alpha t k of x minus the identity times f of x theta t minus y. And you can take the limit as t goes to infinity. In that limit, this term will go to 0. That'll give you how the parameters change as well. And so the interesting thing is that we have a 1 over square root of n power that tells you the parameters don't change much if you have a lot of parameters. Each individual parameter doesn't change much. Okay, there's more on that in the notes, so hopefully you check that out, and hopefully that helped you understand the proof.